Max out GRPO signal, adaptive trace prefix control for hard reasoning problems.
Jamie, what's this hook about making hard problems easier just to get a signal? I'm already confused by the word prefix. What does that even mean here?
Think of it like teaching a robot a tough puzzle. Instead of throwing the whole puzzle at it, you give it a short, correct piece called a prefix.
So they're giving the model a little push at first? But why not just let it figure everything out by itself?
Without help, most models waste time trying to solve problems they can't even begin to crack. It's like asking someone to write an essay when they don't know where to start. They end up doing nothing useful.
The prefix is a kind of starter kit? How does it turn into a full strategy for training?
The starter isn't fixed. It adjusts during learning based on how well the model performs, like tuning a thermostat so heating knows when to ramp up or down.
If you change it too much, wouldn't that mess things up?
They treat the prefix length as something controllable in real time, a closed loop, so the system adapts smoothly to what the model actually needs at each step.
So instead of picking one random starting point, you keep tuning it until things click?
Exactly, that's prefix GRPO. The prefix is invisible when the robot runs in real life. It disappears before deployment.
How does this stand out from other methods?
Many previous approaches either fix a single starting point or give up on hard problems entirely. This method squeezes every bit of learning signal by making the prefix dynamic and responsive.
So they're not just adding randomness, they're actually optimizing something.
They frame it as a controller for success rate, aiming for that sweet spot where you get enough challenge without overwhelming the model.
And they keep everything fair by fixing total compute and using the same data budget across methods?
Yes, no method gets an unfair advantage from extra training time or resources, only the shape of the initial prefix changes.
That's neat. A clever tweak to an existing recipe, rather than starting over entirely.
Precisely. They build on what came before but add enough flexibility to pull more value out of the same training effort.
Next, we dive into the dead zone in group relative RL. Jamie, that sounds dramatic, but it's actually a clever way to describe a specific problem.
Imagine training a robot and only rewarding it for how each rollout compares to others in the group. That's group relative. If no rollout solves the task or all succeed, there's no signal to learn from, like trying to teach someone when everyone agrees they're already perfect or hopelessly lost.
So what happens then? Nothing changes.
Right. And that's why methods like GRPO try to avoid this by focusing on relative performance instead of absolute rewards. But when the dead zone kicks in, the whole system stalls because there's no gradient to push improvement.
So they're stuck at square one.
Exactly. DAPO's dynamic filtering tries to sidestep this by adjusting how rewards are assigned on the fly, recalibrating that balance before it tips flat.
Classical approaches like entropy bonuses or Pascal objectives don't fix this dead zone either.
They help with exploration but don't address the core issue of relative reward collapse. Understanding group relative rewards is crucial for training agents in complex environments where success isn't binary.
So they're looking for smarter ways to keep learning going even when the group hits a wall.
Precisely. And that's what Prefix GRPO tackles next. Adapting prefix lengths based on difficulty offsets.
Sounds like building a more resilient learning loop.
Exactly. They balance exploration and exploitation by keeping success rates near 50%, the sweet spot where each update gives strong signals.
Why does that exact number matter so much?
If you're too far from that middle ground, too often succeeding or failing, the signals become noisy or weak, slowing learning.
So they're not trying to solve every problem perfectly right away. They optimize for steady progress.
That's the idea. By gradually increasing challenge level and keeping the success rate around 50%, they keep the learning process moving forward, even when parts feel stuck in fog. No dead zones allowed.
That prefix trick, adding a hint at the start of a prompt, seems like giving the model a nudge when it's stuck in a dead zone, right?
Exactly. The authors use it to reshape how the model thinks about what comes next without letting the early tokens interfere with learning.
So the gradients are masked on those prefix tokens so they don't disturb the initial part of the sequence?
That's correct. It saves computation and keeps the process stable, guiding the model toward useful paths instead of forcing it to ignore its own hints.
What if the prefix is too long or doesn't match the problem well?
The system tolerates some imperfection. It isn't all or nothing. They've shown it works even when things aren't perfectly aligned, so a perfect setup every time isn't required.
So essentially, the robot learns from its own successes and mistakes, but with enough structure to keep moving forward? So learning isn't always about perfection. Sometimes it's about making every step count.
Right? Finding that intermediate set point turns dead zones into learning opportunities without massive computational power or perfect conditions.
What happens if you overshoot the sweet spot?
Then gradients can blow up, and learning slows because everything becomes too volatile, so hitting the balance is crucial.
They tested this in real experiments with different datasets and baselines, so the findings are solid.
Yes, evidence from multiple studies shows the same patterns hold true across tasks.
Switching gears, how did they train?
They used 3 Quen models, 0.6, 1.7, and 4 billion parameters, from Quen 3 plus Quen 3.5, 2 billion, and Gemma 4E4B to cover different families.
And the training data?
Deep Math 103,000, a set of about 6,000 hard problems with verified answers, carefully chosen so binary answer questions were removed to avoid easy shortcuts.
How did they measure success?
They evaluated how close predictions got to verified solutions across all training steps, also monitoring efficiency and stability. Computational cost was tracked in flops and token counts, treating calibration sweeps as one-time costs.
So accuracy, efficiency, and stability were all considered under consistent conditions.
Exactly. Every method had a fair comparison.
How did the per-sample offsets help keep performance steady across problems?
Offsets narrow the spread of predictions so that not half the batch hits maximum success while the other half fails. They measured variance before and after applying offsets, showing compression without hurting accuracy.
That's a neat way to tune each problem into the sweet spot.
It's a practical engineering adjustment rather than a theoretical overhaul.
Finally, what about baselines?
The authors compared their method against several strong baselines, ensuring that improvements were due to the prefix strategy and not other factors.
That wraps up the main points. Thanks for breaking it down.
Glad to help.
Imagine you're setting up different starting points for a race, and the researchers are testing which one gives the best finish.
Exactly. They compare zero-shot training, just using general knowledge, against vanilla GRPO, the standard on policy reinforcement learning that rewards good actions as they happen.
And then there's the G equals 16 trick, right?
That means they run 16 parallel attempts to speed up training without increasing total computation.
So more parallel work but the same overall effort. Clever.
Right. Now, their main results come from a benchmark called QN3 1.7 billion, where they match floating point operations per second across methods and look at pass 1, which is the percentage of problems solved correctly in one shot.
And 80 Prefix GRPO consistently improves that score compared to vanilla GRPO.
Yes, it adds a measurable bump on several test sets. For example, on Math 500 it gains about 6.4%, and on Deep Math it jumps roughly 17%.
That's a lot of extra solvable problems.
The authors note that simply giving vanilla GRPO more passes or compute only recovers part of the gain. It shows Prefix GRPO reallocates resources smarter, not just doing more work.
So it's about smarter allocation rather than brute force scaling.
Exactly. They even ran control experiments like doubling group size in vanilla GRPO and found the improvements still didn't match Prefix GRPO.
That suggests a structural advantage from the prefix control.
Right. The paper emphasizes that these gains come without increasing model size or total compute, just by reallocating the same flop budget more strategically.
It's like slicing a fixed pie into many small pieces versus fewer big ones. Prefix GRPO chooses slices that improve quality.
And because it focuses on harder problems, it expands what can be solved overall. About 17% more problems become solvable compared to the base model.
That's impressive. Do they back this up statistically?
Yes, they ran paired problem-level bootstrap tests and found significance for most metrics, with confidence intervals around plus or minus 3.1% at the problem level.
So the improvements are robust across different bootstrap methods and tighter statistical checks.
Exactly. They also tested across model families like Qwen3 and Gemma to show the gains aren't specific to a single architecture.
And smaller models benefit more from careful tuning, sometimes outperforming larger models trained without prefixes.
That's right. For instance, a 0.6 billion parameter model with ADA Prefix GRPO beats a 3.7 billion parameter model using vanilla GRPO, even though the compute budget per size is the same.
So the way you allocate passes matters more than raw compute or model size.
Precisely, the authors show that careful allocation can outperform brute force scaling in some cases.
It's a compelling case for smarter training strategies.
And it sets up the next question of how these principles scale beyond current constraints, which they explore in the following parts.
With that in mind, they keep the batch mean ratio K over G steady using a closed-loop controller.
Exactly. The controller constantly nudges the ratio toward half, like a thermostat keeping temperature just right.
So they're not just setting it once and forgetting about it?
Right. They tested several starting biases for the ratio. The default bias of 0.5 proved most effective because it keeps the estimate near zero without letting it get stuck at extremes.
Why does that matter?
Building on that gain we mentioned, a fixed prefix can saturate the system, pushing all samples either fully correct or entirely wrong, which is bad for learning. The dynamic controller avoids that by continuously pulling the ratio back toward the middle.
They also talk about difficulty cohorts. How do those fit in?
The researchers grouped input data by how hard each sample was to predict and then tuned a parameter called ρx, which reflects sample difficulty. By adjusting this parameter, they could drive the K over G ratio toward the target for each cohort.
Did adding an annealing schedule help?
It gave a modest improvement, but wasn't the sole reason for better performance. The main gain came from the controller's steady adjustments.
What about group size? They tested different G values, right?
Yes. Using 8 samples per group hit the sweet spot. Accuracy stayed high while keeping computational steps low. Doubling the group size only halved the number of updates needed but didn't improve accuracy beyond that.
So 8 is efficient and effective.
Exactly. And they swapped in rejection-sampled prefixes instead of standard ones. Performance remained largely unchanged, showing robustness.
That suggests the method isn't fragile to the exact prefix choice.
Correct. They even tested how sensitive everything was to the initial prefix values and found it wasn't a big issue.
So overall, it's about keeping things stable without overreacting to noise or tricky inputs.
That's the core idea. Smart, steady adjustments rather than brute force exploration.
The paper also discusses how the controller reshapes learning. By keeping KG near 0.5, the model focuses on its own successful continuations instead of being distracted by prefix tokens.
Right. The controller effectively creates a signal that resampling alone can't provide. It nudges the reward curve left as policy improves, so training starts from earlier points closer to unprefixed problems.
Even when prefixes are removed, the gains persist because the final pass at one metric still solves many of the originally dead cases.
Exactly. Across tasks, the monotonicity violation rate, where reward changes fail to increase monotonically, was only about 6%, mostly with long-off distribution reference prefixes. When that happened, the controller fell back to a safe bracketing strategy without blowing up.
And the secant fallback rate?
That's the percentage of times the system had to switch strategies, like using a bisection method when things went off track. It occurred roughly 17% of the time, about 4 out of every 24 updates, and only succeeded 3 times in test runs.
So it's a safety net that kicks in about once every 5 updates.
Precisely. The authors also measured how much extra work prefix tokens added, finding less than 15% overhead overall.
That's not too bad.
No, it shows the method is efficient while still robust to different difficulty levels and prefix strategies.
It sounds like a solid balance between stability, efficiency, and adaptability.
That's the takeaway. Dynamic trace prefix control keeps learning steady without sacrificing performance or exploding computational cost.
The authors show that their adaptive prefix keeps search efficient while still enabling deep reasoning, a major advantage for hard problems.
And because they avoid heavy bookkeeping, runtime stays low even as problem size grows.
That makes the method practical where speed matters.
Thanks for listening. Check their paper on Arxiv. Until next time, keep exploring.